So today we're going to finish up a little bit of what we left off with. I also brought a giant stack of textbooks to pull out some problems from, just so that we can get some extra practice in and review some material. Having said that, let's start off with this problem here. What we've got is your traditional piece of paper, right? And inside the piece of paper, we're reserving 24 square inches just to be able to print on. And this piece of paper, top to bottom, is going to have a margin of 1.5 inches. And left to right is going to have margins of just 1 inch. Now what we want to do is we want to play with the dimensions of our paper to figure out how we can minimize the amount of paper used. Maybe we're a printing company and we're trying to figure out how to cut some cost, right? So how are we going to set this problem up? What do y'all think? People at home, what do y'all think? How are we going to set this problem up? All right, well, since nobody has any thoughts on this, the first thing we're going to do is we're going to identify what our unknowns are. And our unknowns here are going to be the width and height of our interior piece that we're printing on, right? So we know from this that x times y is going to have to multiply out to be 24, right? Because the interior here is going to be 24 inches squared. And we know that the entire area is going to come out to be x plus 3, that quantity, times y plus 2, that quantity. Right? Because we have margin of 1 inch, 1 inch, and this thing is going to be y wide, right? So that's going to be y plus 2. And then here we're going to have x plus our margins top and bottom. So that's going to be x plus 3. So what we've got is that x times y is equal to 24 inches squared. And that the area we want to minimize will be x plus 3 times y plus 2. Yeah, I did not reverse it. Good. Now what we're trying to do is to minimize this. So given all of the information we've got, we can start by saying, I can set up a relationship between x and y using this, right? Agreed? So why don't we solve for y here? When we do that, we're going to get that y is equal to 24 divided by x. And now, why don't we plug this into that? When we do, we're going to end up with a is equal to x plus 3, the quantity times the quantity 24 over x plus 2, right? And we want to minimize this. Question, based on what we're doing, can we ever maximize it? Not really, right? Because we can always keep stretching it taller or wider, right? So we can have some crazy length here. So having said that, zooming into what we know so far. So far, we've set up the equation for area. We figured out how to relate x and y together. Then we plugged that in to our area function. When we move through and simplify it, we get down to this 2x plus 30 plus 72 over x. Let me erase what's up here. Once we simplify everything, like I said, we get 2x plus 30 plus 72 over x. All right, quick question. What numbers are possible to, what numbers can we possibly put into this x value?
Zero.
Yeah, absolutely, right? Like we're bounded by the laws of physics here. We can't have negative length. So x, it's going to have to be greater than 0. Now, if we want to minimize this, we don't want to take the derivative with respect to x, agreed? So, dA, dx, this is going to come out to be 2. This is going to come out to be 0. This is going to come out to be negative 72 over x squared, right? So now we want to find a critical point, right? That's what we're asking for when we're minimizing or maximizing, right? We want to find our critical points. So now we're going to set this derivative equal to 0. So a prime is equal to, let's say a prime of x is equal to 0, because it's a function of x, right? So doing that calculation now, we have 2 plus minus 72 over x squared is equal to 0. How are we gonna go about this?
Subtract 2 from each side.
Yeah, subtract 2 from each side. Gonna get negative 72 over x squared is equal to negative 2. We can multiply both sides by x squared now, right? And then divide out that negative 2. Right? So this tells us that x is equal to plus or minus 6, right? All I've done here is subtracted 2 from both sides. Multiplied both sides by x squared, and then divided out that negative 2. So from this, we get that x is equal to plus or minus 6. But we said that x has to be positive, right? So automatically we can throw out that negative 6. Yeah? So from here, to find out what those margins have to be, what that length outside and inside has to be, we just plug in 6 for the length of, the height of the paper. And we plug in 6 over 20, or 24 over 6 in for y, right? So what we're doing now is we're going all the way back to the very beginning. We said, all right, we know what x has to be. X has to be positive 6. Now going back to this length has to be y plus 2, and the height has to be x plus 3, right? So to find out what those lengths are, we just plug in x. And since we've already found that y was equal to 24 over x, we can rewrite the width in terms of x and just solve. Is everybody cool with this? So, checking out another problem. Moving on to section 3.5 and then checking out another problem. This company, let's actually go to another one. I think it'll be a little bit, there's a little bit more going on in this problem, and I think it'll help us think things through a little bit more. So what we've got is this company has found its cost of production function for every X number of things it makes. So what we're saying here is, I'm a company, I'm going to produce 12 things. This tells me how much that's going to cost. Now what we want to do is find how many X values of items we have to produce to minimize the average cost. So this is bulk cost, right? Average cost is going to be this divided by X. Agreed? If that's going to be bulk cost, if this function up here is going to be bulk cost, that's the cost for everything. Then the cost per item is going to be that divided by the number of items, or X. So let's go ahead and define that up here. We've got C is equal to 800 plus 0.04x, excuse me, plus 0.002x squared.
It's 0.0002.
0002. Thank you. All right. So, if this is, again, the bulk cost, the average cost, or cost per item, is going to be this divided by x. Or 800 over x plus 0.04 plus 0.0002x. Yes, ma'am.
So the zero words before the x disappears.
I'm sorry, what was that?
The x disappears there.
I still didn't.
Oh, so where the 0.04, the x disappears, is that the same x that goes down, or is it just a formula?
That's that. So I think I see what you're saying. So what's happening here is we're going to be dividing this by x, right? So we're going to have that 8 divided by, or that 800 divided by x. This x is going to be canceled out. And then this is going to be lowered by a power. Does that answer your question?
Yes.
Yeah, awesome. All right, so now we've got the average cost. Next question, what can x be? What values can x take on? Anything 0 or bigger, right? Like we can't produce negative items. So x is bigger, is equal to or bigger than 0. Now looking at this, they have a typo in here. This should be C bar. Excuse me. C bar is the function we just defined up here. And eyeballing it without them telling us exactly where the min is, it's kind of hard to see where exactly that min occurs, right? So again, to find this, we're going to apply the derivative, set it equal to 0, and then solve for what that x value has to be. So we know we have to produce something more than 0, right? Their argument for why it can't be 0 is because 800 divided by x, if x were 0, can't give us a value. Okay, so having said that, taking the derivative of both sides, we're going to get negative 800 divided by x squared plus 0.0002. That's the derivative here. Right? And then they set that equal to 0, and they solve. And when they solve, they find that x is either equal or is equal to plus or minus 2,000. But we said x has to be greater than 0, so we take 2,000, and that's the min. So having said that, I want to get us through some of these definitions as fast as possible so that we can get to a review point. Yeah, let's skip now to the definition of the price of the elasticity of price of demand. Definition of price elasticity of demand is what I'm trying to say. We write it with the Greek letter eta, and we say that eta is equal to price divided by x divided by the derivative of price with respect to x. So x here is demand, right? Everybody cool with that? X is going to be demand, so we have price divided by demand, that thing divided by the derivative of our price function with respect to demand. We say that the demand is elastic if eta is greater than 1. It's inelastic if it's less than 1. And it has unit elasticity if the absolute value is equal to 1. I'm sorry, I should have said the absolute value of eta is greater than 1. The absolute value of eta is less than 1. And the absolute value of eta is equal to 1. Is everybody cool with this? So let's just jump right in and start using it now. We're told that price as a function of demand is equal to 18 minus square root of x, that quantity times 15, right? Or I mean 1.5, not 15. I think it's time for new glasses. So what we're told is that P as a function of x is equal to 18 minus 1.5 times the square root of x. Now, I personally would like to break this problem up into two different parts. Since what we're trying to solve for is eta is equal to P over x divided by dP dx, I'd break it up into two parts. I would go ahead and solve for this, and then solve for this, and then put them back together. So, P over x, it's going to give us 18 over x minus 1.5 divided by the square root of x. Yeah? And now the derivative of this is going to be what exactly here? What do y'all think? Based on the power rules and everything else that we've done before. This doesn't exactly help. Let me rewrite this so we can see why. 18 minus 3 over 2 x to the 1/2. Well, we're going to lower this by a power, right? We're going to multiply this by 1/2. That's going to be it, right? Because of the power rule. We're going to take the power, multiply by it, and then lower the power by 1. Yep. So this thing is going to come out to be negative 3 over 4 x to the negative 1/2 power. So when we put all of that together, we're going to get that eta is equal to this crazy fraction that it's terrifying. But we're going to be able to simplify it some. When we simplify it, we're going to find that it's equal to negative 24 times the square root of x divided by x plus 2. Everybody cool with this? We could simplify this a little bit more. Because if we multiply this by the square root of x over the square root of x, this will become x, right? Divided by x. We'll have just the square root of x underneath. So we could simplify it a little bit more, but let's leave it here. So, I did not mean to press that button. Going back to the problem, we're asked now to find the intervals on which the demand is elastic, inelastic, and of unit elasticity. So what we're looking for this was negative 24, right? Square root of x over x plus 2. Is that right? Yeah. What we're looking for is when this thing eta, the absolute value of eta is greater than 1. The absolute value of eta is equal to 1. And the absolute value of eta is less than 1. These are the three cases we're looking for now, right? So we're going to take the absolute value of that function we found, set it equal to 1, and then use that to break up when it's less than or equal to or greater than 1. Does that make sense what I mean? So eta is equal to 1 in the interval 0 to 104 or to 144. My mistake, when x is equal to 64. We're trying to find the unit elasticity in the interval 0 to 144. So the only number that will make the absolute value of eta equal to 1 we'll solve to find is 64. So that means our intervals that we're going to be breaking up now will be 0 to 64, 64 to 144, right? Make sense? So there, we're just going to check a number in those intervals and say, all right, in these intervals, what's what? It'll make it a little bit easier on ourselves that way. Cool with this? From there, we're gonna find, okay, it's inelastic from 64 to 144. It's elastic when X is between 0 and 64. Now going back to the original question, we just found this part. And the way we did it was by answering the unit elasticity, because that was going to be an easier question for us to answer. And then using that to inform where to check. Make sense? Now, the second part is going to be to use this to describe the behavior of our revenue function. But just for the sake of review, what's your revenue function?
Price minus cost. Or
Profit minus cost. But in this case, they're going to say that it's the price of the good as you sell it times the number of goods you've sold. Make sense what I mean? So with that, because what the demand function is telling us is the outward facing cost of the product. So what the consumer sees as the price of the product is what the demand function is going to tell us. So that P value is the actual price at user cost. So that times the number of items you've sold is going to give you the revenue. So here, I think I actually said that backwards a second ago. It's profit is equal to cost minus revenue. I think I said that backwards a second ago. But here, we're looking at, again, the revenue. So the revenue here looks kind of like, well, kind of like a parabola. Notice that it peaks at 64, where we had unit elasticity show up. So this elasticity function is telling us something about the revenue function, right? So what they're going to tell you is that we can determine on the open interval from 0 to 64, this thing is going to be increasing. And 64 to 144, this thing's going to be decreasing, these functions. Does that make sense? Which jives with what we were seeing in that picture, or in that graph. Now, as a quick review of all of these different business terms. The number of units produced will usually represent as an X. The price per unit will usually be represented as a lowercase p. The revenue will be X times the price per unit. The cost, well, that's just the total cost of producing, capital C. Capital P is going to be your profit, that's revenue minus the cost. Cost per unit, that's going to be represented using a C bar. And that's just the cost of production divided by the number of units you produced. Elasticity, we just talked about. Marginal revenue, marginal cost, and marginal profit are all the derivatives with respect to the number of units produced or sold. Yeah. So generally speaking, we're going to find that the demand function, the quantity demanded increases as the price decreases, right? The other way to say it is that the cheaper the thing is, the more people are gonna buy it. McDonald's gets away with making all of their $1 things because they're so cheap, right? People are going to demand more of it. Partially because more people can buy it, and then partially just because, well, it's a cheap alternative to, I don't know, Outback Steakhouse. Because that seems so comparable, right? Revenue function, similar idea, but we're going to find sort of the reverse situation here. Y'all don't need me to reread these to y'all. I hate instructors who read straight off their slides. So if y'all catch me being like, let me just regurgitate what's up here to y'all, please stop me. All right, cool. So we've got 39 minutes. Having said that, I want to open up the floor to questions really quick. Do y'all have any questions about the material thus far? Exam 2 is next week, so that's why we're doing this now.
When next week is exam due? Do you know?
Weekend.
Weekend.
Yeah. I'm not going to give y'all exams during the week, and I'm not going to give y'all exams at the beginning of a week either, because like that's just a great way to ruin a weekend. But if I give y'all Friday, Saturday, Sunday to do the exam, that's on y'all when you want to get it done. It'll be same format as the last exam, 90 minutes online. I just discovered in my other class, apparently somebody's computer crashed in the middle of the exam. If that happens, let me know. I'll work with y'all. I'm not an absolute ass about this stuff, right? If things happen, they happen. I get that life gets in the way sometimes. So that exam, like I said, will be 90 minutes. You'll have Friday, Saturday, Sunday. I'm putting up a study guide. What else do I want to let y'all know about that? I haven't posted one yet, but I'm going to. Thank you. Yeah, that's all I have in that way. What about y'all? Any questions thus far about material? Right? This cone has a volume equal to pi over 3 times r squared h. Don't feel bad if you don't have that equation memorized, because neither do I. And it is being filled up at a particular rate. Being filled up. Where's the rest of that problem? Wow, this is awesome, guys. 2 calc books with almost identical, there it is. Okay. We are told that the rate with which the radius changes with respect to time as this is being filled up is equal to 2 inches. We are told that the height of this cone is equal to 3r. And asked to find what is dV dt when r is equal to 6. All right, so what we're doing here is we're filling up this cone, right? The height of the water is going to be increasing. As it does, so too does the radius of the cone, right? At the top of that water height, right? So this area here, this bit, has some radius associated with it with that height. We know that dr dt is equal to 2 inches. This is the rate at which the radius is going to change with respect to time. We want to know what the rate of change of the volume is going to be, given that r is equal to 6 inches. So how are we going to go about this? What do you all think?
We have plug H in.
Yeah. First thing we're going to want to do, plug H in. Because we know H is equal to 3R, we know volume is going to be equal to pi over 3 R cubed times 3, right? So let me write it the other way and then simplify it. R squared times 3R. Well, this is going to cancel with that. We're going to be left with pi R cubed. Everybody agree with this? Okay, now we want to find out what dV dt is. Well, in order to find it, we're going to have to apply the chain rule here, right? So, finding all of this, setting up a nice little area to work in. We're going to take d dt of v, which is equal to d dt of pi r cubed. This thing is going to come out to be pi times 3r dr dt. Everybody agree? Well, we're given that the change in radius with respect to time is 2 inches per second, right? I forgot to write it per second here. So we're going to have to plug that in now. This is going to get plugged into here. All right, so this is going to come out to be 6 pi r. Everybody agree? My mistake, r squared. Forgot to square on this. Is everybody cool with this? So now we want to know what dV dt is when R is equal to 6 inches. So when we get to this point here, right, and it's equal to 6 inches, we're just going to plug 6 in now to find out what dV dt is. I have no clue what 6 cubed is, so don't feel bad if you don't either. This thing is going to be equal to the change in volume with respect to time when the radius is equal to 6 inches. Here, let me write it a slightly different way. dV dt at 6 inches is equal to R. Does this problem make sense to everybody? Okay. I wanted to go over at least one of these just because, like I said, I noticed in the homework, there were some hiccups with it. What we're doing with these is we're applying the chain rule, right? We're going back and saying, based on the initial equation that we're given, we're trying to find something out. In our case, we're trying to find out what dV dt is. And all of our unknown variables in some way relate to time or something else that relates to time, right? So for example, we're told that h was equal to 3r here. So 3 times the radius. And we knew that the radius, the change in the radius, wherever the top of the water level is, that was changing with respect to time at a rate of 2 inches per second. We said, all right, well, that means h is somehow related to time, r somehow related to time. We want dV dt. Cool. Let's apply chain rule. Applying chain rule, we got pi r squared times, or my mistake, pi r cubed, right? Applying chain rule then gave us pi 3r squared dr dt, right? Plugging in what we knew, we were able to solve the rest of this problem. Does this jive with everybody? Yeah, okay. All right. Got a box. That's a box. Got a box with surface area equal to, I'm going to write it as S dot A for now, surface area, equal to 244. We want to know what the maximum dimensions are, or what dimensions rather will maximize the volume of this box. First thing we need to know about this box is that it has a square base. So since it has a square base, this is going to be of length x, this is going to be of length x, right? That means this is going to be of length h. And when we unfold it, it's going to look something like this. each of these flaps are of length h, and this is of length x, this is of length x, right? Because we're just folding it up. So the surface area then is going to be equal to the equation x squared, right? Because that's the area inside of this, times the area of each of these flaps is going to be xh. So plus 4xh. Now, going back to the original picture of the box has volume x squared times h. Agreed? Because it's going to be the surface area raised through, extruded through the height. Yeah? So from here, we know that this thing or xh is equal to 244, which is going to let us set up a relationship between x and h, right? Setting that up, we're going to get that h is equal to 244 minus x squared divided by 4x. Yes, sir.
Wouldn't it be a 2x squared because the top and the bottom of the box?
It's an open box.
Oh, okay.
Sorry, I should have probably said that, made that part clear. Yes, it's an open box. There's no top to it. Otherwise, you would be absolutely right. So here, we've got, like I said, 244 minus x squared divided by 4x. 244 is divisible by 4, agreed? It's going to be 61, right? What I'm saying is we can simplify this. We're going to get 244 over 4x minus x squared over 4x. This whole thing is going to come out to be 61 over x. Minus x over 4. Yep. All right. So let's replace our h up here with 61 over x minus x over 4. This will just make the math easier for us in a minute. Now, we want to know the dimensions to maximize the volume, right? So that means we're going to have to take dv dx or dh, presumably, to maximize the volume, agreed? Well, since we just solved for h, let's go ahead and throw that into our volume function. Volume now is going to be equal to x squared times the quantity 61 over x minus x over 4. Well, we can simplify this. So let's go ahead and do that. When we simplify it, we're going to get 61x minus x to the third divided by 4. Everybody agree? People at home, still with me?
Yes, we are.
Awesome.
Yeah.
Dope. All right, so from here, we're going to want to take the derivative of our volume with respect to x. Everybody cool with this? Let me erase some of this to make more room. So we're gonna have dv dx is equal to 61 minus 3/4 x squared, right? Well, let's set that equal to 0. We want to maximize this. When we set this equal to 0, we're going to find that x squared times 3/4 has to be equal to 61, right? Excuse me. This is going to let us solve for x. I'm going to erase all this over here, just so we have that there still. (61 minus 3/4 x squared is equal to 0. This is going to give us that 61 is equal to 3/4 x squared. Multiplying both sides by 4, and then dividing by 3. (244) divided by 3 is equal to x squared. That's not divisible by 3. So now we just take the square root of both sides, right? And we take the positive root, the principal root. This is going to tell us that the square root of 244 divided by 3 is equal to x. And we want to take the positive root here, because we have to use positive values, right? Because x has to be something meaningful, something real. Make sense? So now from here, we found x. We plug that back in to h, into our equation for h, to solve for h. Yeah? And that'll tell us what our dimensions have to be. People at home, do y'all have any questions about the material thus far? Like, not necessarily about this problem, but just about what we've done in class.
To clarify the date of the test, is that the 26th through the 28th?
I'd have
So
to
not okay. So not like this upcoming weekend, but the weekend after.
Right, not this weekend, next weekend.
Okay, cool. Just making sure.
Yeah, not this weekend, next weekend. And in the meantime, between now and then, I think we have only 2 or 3 more things that we're going to be going through from this point on, just until the test. We have, I think, 3.6, 3.7, and 3.8 that we still have to go through. But like I said, I just wanted to take this moment to kind of look back at some of what we've done. It seems like a natural stopping point to be like, all right, what's going on here? Are there any hiccups? Is there anything that we don't understand? Having said that, unless y'all have questions, feel free to go.